T inverse V, and hence this would be equal to the magnitude of V. Okay, this is equal to the magnitude of V because this will become identity map. And now I know about the T, that my T is an isometry, so this means that this must be equal to T operated onto V, the magnitude of V. And if this is the case, then what is T of V? The T of V is U. So what we actually showed that if T is a linear transformation, T is an isometry, we know it's 1, 1, and hence it must be onto, then its inverse is also invertible, is also an isometry. Okay, so the T inverse operated onto U gives back the magnitude of U. So these are some of the basic properties of basic properties of the isometries. Here is another interesting basic property which can be also treated as that T is really a distance preserving map. Actually, isometries are the distance preserving map. Okay, I'll prove this identity or the result in case of this field of complex field of real numbers, and you have to do it for field of complex numbers. So here is another interesting property which says that if T is an isometry from say calligraphic V into calligraphic V, where calligraphic V then the product space, isometry, then not isometry. So it's I'm going to say, alright, so I can say it's an isometry if and only if. Obviously it must be a linear transformation. Okay, so you have a linear transformation, that linear transformation is isometry if and only if. So there is a characterization. So this is, you can also treat as it, the statement that I'm going to write as a definition of isometry actually. Okay, it's equal to Tu dV, okay, equal to U V. In other words, for all U and V from calligraphic V. Okay, so what does this shows? This shows that a linear transformation, okay, I must write, okay, so a linear transformation T from inner product space V to V is going to be an isometry if it not only preserves what you call sizes, but it also preserves inner products actually. That okay, you take two vectors and compute their inner product before transforming them, and compute their inner product after transforming them under the T, that they should be equal. And if this is happening, T is an isometry, and if T is an isometry, this must happen actually. Okay. This must happen. So here's a proof of it. So let's first say think about the converse of it, that why, if this is true, should be an isometry. Okay. Now, if I use this identity for U, okay, from the calligraphic V, then I know that this, and if this identity is true, then this Tu, this will be equal to Tu, and UU. So this is true for all U and V. So if I take V to be also U, then I'm going to have this identity. And if this is true, this is equal to the magnitude of Tu square, and this is equal to the magnitude of what you call U square, and taking the square root gives you Tu equal to the magnitude of U, and this shows that T is an isometry. Okay, so it's an isometry. So if this holds, T is an isometry. Now I'm going to show the forward statement, so that if T is an isometry, this must be true. I'm going to prove this for a set of real numbers, okay, using the so-called polarization identity that we proved when we did the theory of inner product spaces. So you have to do it for yourself using the polarization identity for the field of complex numbers actually. Okay, you can read its proof from the notes. Alright. So for real numbers, using so-called polarization identity, I want to deduce this. So what is polarization identities? The polarization identity tells you that if you have Tu Tv, this is equal to 1/4. In fact, if I write first polarization identity, the polarization identity tells you that the inner product, the real inner product of UV is equal to 1/4 times of norm of U plus V square minus norm of U minus V square. Okay, so if you compute norm of U square plus norm of U minus V square, you're going to get 1/4 times of inner product of UV. So this is the identity. Let's apply this polarization identity when the U is okay. So let's apply this polarization identity in the case when U by replacing U and V by DUV. So we kind of recalled our polarization identity, okay, and now let's apply this for TU and what do you call TV. Then by polarization identity, this will be equal to norm of TU plus TV square. By the way, this polarization identity is true for all U and V in the inner product space V. Okay, so this is true for all U and V in the inner product space. Square U plus P of U minus V square. So this is true. Now I'm going to use the linearity of the transformation and the isometry of it. So by linearity, I can write this T of U plus T of V as T of U plus V magnitude square plus this is going to be T of U minus V magnitude square. Actually, I hope you agree with me. And now since T is an isometry, okay, so this is equal to norm of U plus V square plus or minus, I think this should be minus norm of U minus V square because T is an isometry. Now again, using the polarization identity, this is precisely equal to norm of UV. And this is what that you would like to show actually. For all U and V, the polarization, for all U and V from the inner product space V, the inner product of UV and transformed UV is equal. Okay, so the inner product is kind of invariant under the transformation. So that's another interesting thing. Let me list another theorem. Okay, so I'm going to list all of the basic properties of it and then do some of the examples or the uses of it. So here is another interesting result which is true in finite dimension. So imagine that nu be finite dimensional inner product space. Okay, and T is a linear transformation, and T is a linear transformation. Then here is another characterization of an isometry. Then T is an isometry. Isometry if and only if you take the adjoint of that isometry and compose it with what do you call the transformation itself, you can get what do you call the identity transformation actually. Okay. So in other words, you can say that the adjoint of the transformation, we defined the adjoint in our last class. The adjoint of the transformation is like the left inverse of the transformation T, or of the transformation of the isometry T actually. Okay. So this is what is another characterization of isometry, that you can identify the isometry from its magnitude. Okay, from its adjoint. So here's a quick proof of it. So let's prove this actually. So suppose that the adjoint of the operator is the left inverse of the linear transformation. The thing that I have to show now is that it must be an isometry. Okay, the T must be an isometry. Now, how I'm going to show it? Let's just start with, say, magnitude of U. Probably it's a square. I would like to show that this is equal to the norm of U square. Now I can show this as, okay, T, this is same as the inner product of TU with TU. And T is the adjoint, T star is the adjoint of it. So I can write this as U adjoint of T operated onto U actually. So this is what the basic definition of what you call adjoint is, that you know the relationship between adjoint of an linear transformation is that TUV is equal to U T star V for all UV. Okay, so this is what is the relationship between the adjoint. Okay. So, and I know about this that my assumption is that this is identity, so you get what we call norm of U, which is equal to the magnitude of U squared, and that shows that T is an isometry. Okay. Now let's prove this in forward manner, and let's assume that T is an isometry. Why the adjoint composed with the transformation is going to give you the identity. So suppose that T is an isometry. So let's apply T star T U onto what do you call it? Okay, so I'm going to prove this side. So let me write it that T is isometric. Suppose that T is isometric. And I want to show that T star T is an identity matrix. So what I'm going to show, so this is what is going to be the case. T star T operated onto U, and let's take its inner product with V actually. Okay. And then by definition of adjoint, if you throw this on the other component, it's going to be TU, TV actually, okay, by definition of adjoint. And if this is the case, and T is an isometry, then by this result, this is equal to, what do you call it, UV. And what does this shows? Okay, what does this show? I can, if I bring this on other side, and I can show that, okay, so the T star TU minus U V is equal to 0 for all vectors V in the inner product space V. And we know that if this is true, then okay, so this is a vector that is orthogonal to entire inner product space actually. So what is the vector that is orthogonal to entire inner product space? So this vector must be equal to 0. And if it's 0, what follows from here is that T star T operated onto U is equal to UN. And hence, this shows that T star T operated onto it is an identity. Okay, is an identity. So these were some of the basic properties of isometries. So we showed that an isometry is distance preserving map, it's a magnitude preserving map. Composition of isometries is isometry. Isometries are always 1, 1, and hence they are invertible. And the inverse of it is also isometry. And then we kind of had two characterization of isometries, that an isometry is inner product preserving map, okay, and an isometry is such a map for which the adjoint composed with the transformation or itself is always identity. So in other words, isometry is kind of is a left inverse, or the adjoint is a left inverse of the isometry. Okay. Unitary matrix is a matrix. I'm going to put it in a moment, but you can also relate the unitary matrices with the isometry. So in other words, if you take an isometry and consider its, say, matrix representation, that matrix representation is going to be a unitary matrix. And if you have a unitary matrix, and if you consider its, what do you call, linear transformation, corresponding linear transformation, obviously you are in finite dimension, then that linear transformation is going to be an isometry. Or here is one way to describe them, that we are interested in such n by n matrices corresponding to which the matrix, the transformation corresponding to the unitary to the matrix U, okay, onto, say, in a product space V, obviously in a product space is finite dimensional, are isometries, is isometry. And so they induce, so matrices that induce isometries, okay, so they induce isometries. So here's a clear definition for it actually. That you're gonna say that a square matrix, okay, a square matrix U is unitary if the T is an isometry. What does this show? That the conjugate, the adjoint of it composed with T should give you identity. So what would be the analog of this? The analog of this is going to be that if you consider the U star of this matrix and multiply it with U, you should get an identity matrix with N actually, where the U star, as we know, that it's the conjugate transpose. Okay, so it's the conjugate transpose. So what's the unitary matrix? So it's a matrix U. If it's conjugate transpose multiplied by U gives you identity matrix. And we actually saw previously that in case of the matrices, if you consider the adjoint of the matrix corresponding to the adjoint operator is basically the conjugate transpose matrix, actually, the U star. Okay, so we saw this in our last discussion as well. So what's a unitary matrix? It's a matrix for which U star U is an identity matrix, actually. Obviously, this is the case when the U has the complex entries, actually. But a real unitary matrix, is a matrix which is orthogonal, okay? A unitary matrix is real unitary matrix is real orthogonal matrix. And what do you mean by orthogonal matrix? That if you take the transpose of it, okay, and multiply it with the U, you should get an identity matrix. So the transpose is like the inverse of the matrix, actually. Okay? So if you have a complex matrix, then unitary matrix is a matrix for which the conjugate transpose, the U star U, is identity. And if you are talking about, say, real matrices, then unitary matrices are basically orthogonal matrices, actually. Okay? They are the orthogonal matrices. What are some of the examples? Some of the interesting examples from, say, the physics, actually. So in quantum mechanics, these spin matrices, poly-spin matrices, play an interesting role. So poly-spin matrices are examples of what do you call unitary matrices, actually, complex unitary matrices. So spin around these matrices: sigma x 0 1 1 0, sigma y. Okay. What do you call 0 minus iota 0? Sigma z spin matrices. One half particle, okay, is 1 0 0 minus 1. You can verify that these three matrices are these two are real orthogonal matrices, while this is a unitary matrix, actually. All three are unitary matrices. Okay, so real orthogonal matrices is also a manifestation of unitary matrix. You can put them in a single category. Okay. And these matrices are pretty interesting kind of a matrices, basically. Okay, why? Because the equation, the Pauli equation in the terms of these matrices satisfy what you call the non-relativistic version of the Schrödinger equation, actually. Okay, and they kind of represent the spin of. So spin 1/2 particle, okay? So not a surface guy, but okay, spin 1/2 particle in an external electromagnetic field. Okay? Electromagnetic field. So that's one of the interesting examples of unitary matrices from the quantum mechanics. Quantum mechanics is filled with such matrices. Next is another example could be, say, consider a matrix in which you have, say, consider a diagonal matrix in which you have, say, e to the iota theta 1, so it's a diagonal matrix, e to the iota theta 2, and e to the iota theta n, and and this and this are 0, you can also verify that these matrices are also what do you call unitary matrices actually, because if you compute its conjugate first of the each term and then transpose it and then multiply it with the D itself, then you're going to see that you're going to get an identity matrix actually. Okay? So that's another example of unitary matrix. I mean, the more familiar and famous example is what you call the plane rotations actually. Okay? Plane rotations. Okay, so for example, if I have a vector, a position vector of say, a point xy, and you want to, for example, rotate this vector by some angle, say theta. Okay? So you want to rotate this vector xy by some angle theta. So then what you can do, that you can take this vector and multiply it, say for example this matrix actually, okay, which is usually called the rotation matrix actually. So the u of theta, so it goes like cos theta, okay, minus sine theta, okay, sine theta and cos theta. Okay, so you can do what, that okay, you pick a vector actually, okay, and say for example multiply that vector with say this matrix. So it's going to take that vector and going to rotate it, what do you call, with an angle 90 degree actually. Okay, angle 90 degree. For example, let's say you can verify that this is a unitary matrix. Okay, so I'm not going into these elementary calculations. You have to do it for yourself. Obviously, these all four are real numbers, so this is an orthogonal matrix actually. Okay, that's a real orthogonal matrix, or unitary matrix. You might have seen this in your first linear algebra course as well. That if you take, say, a vector, okay, let's say, which is kind of a position vector of a what do you call a vector which is 1, 1, for example, okay, which is referring to the point 1, 1, in other words you have this vector 1, 1, and you take this vector and make a 90 degree rotation. So what are you going to get actually? You can already guess that you will get